Hello, we are Group 12 and this is our final project presentation for CS4640 Health Informatics. Our project is a blood cell detection system with FHIR integration. The main goal of this project is to connect AI-based blood smear image analysis with standardized healthcare data workflows. In many healthcare settings, blood smear images are reviewed to identify and count different types of blood cells, such as red blood cells, white blood cells, and platelets. These results can provide important information about a patient's health condition. However, image review can be time-consuming and expensive, especially when patients need frequent monitoring. For patients with chronic conditions, repeated testing and review may be necessary over time. Frequent visit, manual review, and disconnected data system can make this process less convenient for both patients and healthcare providers. For this project, we want to build more than just a computer vision demo. We want to create a system that shows how an AI detection result could become part of a healthcare workflow. To do that, we built a web application that allowed users to upload blood smear images, run image detection, and view detected blood cells, and connect those results to FHIR resources. Our goal is not to replace the medical professionals. Instead, the system is designed as a proof of concept tool that could support faster review, better organization of results, and a smoother integration between image analysis and health records.
One technical improvement in our project is the image analysis model we select and how it fits into the full systems. In our project, the detection model used DNL-V2 as the visual backbone. DNL-V2 is a visual transformer model, and in our system, it is used for feature extractions. This means that instead of directly classifying the image from scratch, the model uses DNL-V2 to capture important visual features from the blood smear image, such as cell shape, texture, and boundary. On top of DNL-V2, we built a customer transformer-based detection head. This detection head takes the visual feature from DNL-V2 and turn them into detection result. In another word, it helps the system identify where the blood cells are located and what type of cell each one is. The model detects three main blood cell classes: red blood cell, white blood cell, and platelets. After a user uploads a blood smear image through the web application, the system analyzes the image and returns an annotated result. The output includes bounding box and a segmentation mask around detection cells and account for each cell type. This model choice is important because blood smear image can be visually complex. Cells may overlap, touch each other, or appear very close together. A simple image classification model will not be enough because we do not only need to know whether an image counts blood cells, we need to know where each cell is located and how many cells are in each type are present to avoid the double counting. The model was fine-tuned on the blood cell detection dataset from RoboFlow Universe, which contains 364 annotated blood smear images across the three cell classes. This dataset allows us to train a model from our specific task instead of using a general-purpose image models without adaptations. Another important part of the technical design is that we use the RoboFlow SDK to support dataset download, augmentations, and versioning. This helps make the dataset prepare properly more organized, since the medical image dataset can be limited. Augmentation is useful because it can create variation in the training dataset and help the model become more robust. For model training, we use Python, PyTorch, and Google Colab. PyTorch serves as the deep learning backend, where Google Colab provides the GPU environment needed for training. After training, the model output was connected to the rest of the system through the web API. We also use the supervision library to manage bounding box annotate and visualization. This is important for the user interface because the user needs to see not only the row count numbers, but also where the model found each blood cell in the image. The annotated image makes the AI result easier to interpret and verify. From a health information perspective, the model design is important because the quality of the AI output directly affects the quality of the structured healthcare data we create later. If the model produces inaccurate detections, then the FHIR observations and the diagnosis report will also be less reliable. Therefore, improving the image analysis step help make the overall FHIR workflow more accurate and useful. In our FHIR mapping, the lab is represented as an organization, the upload blood smell image are represented as a media, and the detection result are represented as observation and summarized in a diagnostic report. We also support both Lab Connect and the manual upload workflow, and both workflow produce standard FHIR results. For the final result, the model reached a precision for approximately 92%, which exceeds the original target of 85%. We also checked the class distribution across all data split and confirmed that the augmentation pipeline was working correctly. Overall, this showed that the model was not only successfully trained, but also performed better than our initial goal while supporting the rest of the application workflow.
Now we will show the demo video of our application. In this demo, we will walk through the main workflow of the system.
Our project has three main functions. The first one is a lab FHIR workflow. In this workflow, we can look up a patient through FHIR, load recent blood smear images from FHIR media, run detection on one select image, and then upload the result back to FHIR as observation resources. The second one is patient upload and file record. Here, users can upload their own images, run detection on multiple images, see the annotated results and total counts, export the results as CSV, and also upload a summary to the patient's file record. The third part is analysis and CSV export. This is a simpler standalone workflow for running detection, checking results, and exporting CSV files.
Our first project success is more accurate cell detection. The model combines bounding box detection with cell-level localization, so it can identify both where each cell is and what type it is. This is important because blood smear images can be complex, with cells overlapping or appearing very close together. By detecting individual cells, the system can better identify platelets, red blood cells, and white blood cells, and produce clear results for the later FHIR workflow. Our second project success is that the model can work with relatively small training set. This is important because labeled medical images are often difficult and time-consuming to collect. It is also useful because different labs may have different blood images. Since the model can be fine-tuned with a smaller amount of labeled data, it can better adapt to local lab conditions in future use.
If we were to continue developing this project, there are several directions for future work. First, we would improve model evaluation by testing the model fine-tuning ability across the blood cell image, prepared with different smear method. We would also evaluate whether the model can achieve strong performance with a small few-shot dataset, such as 15 images, to better understand the model's ability. Second, we would improve clinic validation. Since this project is a proof of concept, we use mock patients for testing. Future work will require collaboration with client experts to evaluate whether the detection result and the FHIR reports are medically meaningful and useful. Third, we would improve the user interface. The current app shows the main workflow, but the future version could include better result explanation, confidence scores, trend visualization, and clear patient history views. Finally, we will explore deployment improvement. With model compression, quantization, or edge deployment, the system could potentially run in a lower resource setting. This could make the technique more accessible for small clinic, remote care setting, or mobile health application. Overall, the future goal would be to make the system more accurate, clinic validate, and better integrate into the real healthcare workflow.
To conclude, our project is a blast cell detection system with fire integration. Each team member's contribution is on this page. We built this project to explore how AI-based blast smear analysis can be connected to standardized healthcare workflows. The system detects platelets, red blood cells, and white blood cells from microscopy images, then maps those images and results to fire resources, such as media, observation, organization, and diagnostic report. Through this project, we learned that building a healthcare AI system requires more than model development. It also requires careful workflow design, data standardization, system integration, and validation. Thank you for watching our final project presentation.